So, Alexa, you can start.
Okay, so it's my pleasure to introduce Camille Laurent from Metz University, and he will talk about foliations and related things. It's a joint work with Ruben Lewis, his former PhD student Leonid Ryvkin, and Simon Fischer. So it's my pleasure to start the talk. So please, Camille.
Thank you very much, Alexei, for for introducing my lecture. In fact, I will mainly speak about a joint work with Simon Raphael Fischer. Do you hear me well to start with?
I do.
Yeah, me too, yes.
And well, I will start by maybe 30 minutes of a general introduction to the topic of singular foliation. Then I will introduce one theorem I got with Leonid Ryvkin and present the result we got about Leonid Fischer. So singular foliations, well, I think you are probably familiar with differential geometry. So you're probably familiar with regular foliations, which is a very nice and very developed theory. And well, singular foliation, as you may expect, are foliations, but where we allow leaves, but we are allowed to have some types of the singularities, not all types. And it's a very old area of research. It started like in the 50s, even probably earlier. That got developed a lot in the 60s, but somehow got forgotten. And now it's coming back and under pressure of non-commutative geometry. But what is interesting is that it has always been around, but it was always seen like just when a foliation is singular, is just a very boring set of leaves where nothing can be said. But I always do the joke when you look more carefully, you might see snakes. I mean, do you see the snake on the picture here? I think it's exactly that. It seems to be trivial, but when you look more carefully at it, you really see like weird things, weird phenomena, difficulties, and so on. So I would start by explaining our opinion on what a singular foliation has to be. Because one of the problems of the area is that somehow there are too many definitions around. But very briefly, like in 5 minutes, explain why it's interesting to study them. And then I will explain the problem of neighborhood of leaves. So actually with Ruben Louis and Ruben Ryvkin, Leonid Ryvkin, we are trying to write a book about singular foliation, in particular to fix vocabulary. So to start with, what are they? So they here is singular foliation. Well, I will give 3 successive definitions. The first one is just very bad. It will be my first attempt. And I will not call them singular foliation. I call them partitionnifold. Well, you take a manifold M. M is any manifold here. And what you call partitionnifold is just that you partition M into immersed and connected sub-manifolds that you call leaves. And well, this definition is extremely useful. It's useful to have a word to say it, but it's not interesting. It's not how we should define singular foliation. It's way too wide. Let me introduce a notation because I will use it many times. A partitionnifold, I will denote it as a map from M to submanifolds of M. Well, connected and immersed, but I don't write it. It go like this, that to a point M associates the leaf through its LM. Well, what is the problem with that? The problem with this definition is that you have too many examples that you don't want to see. What you don't want to see, for instance, is what we call isolated lasagna, which means you are in R3. You have one leaf, which is a horizontal plane, and the other leaves are just straight lines. So like an isolated lasagna in a spaghetti dish. That's very bad. But you have even bad example where all leaves all have the same the dimension. Like look at this one. Again, we are in R3. You have a circle like this. Then you take all the leaves of all the trajectories of a magnetic field. If you imagine that you have an electric current in here. Well, I mean, I'm not saying it's not interesting to study it by itself, but this kind of things, we don't want to study them. There is really nothing very interesting that we can do with these things. We are much more interested in singular foliation like this one. You take a straight line, and around it, you take the cylinders like this that are somehow rolled along the straight line. And well, that's much better. And you see that you have two kinds of leaves. This one, it's obviously a singular leaf because it has the dimension 1, right? While all the cylinder around, they are all regular leaves, because when you take away the straight line here, you just get a regular foliation. So now, how to make, oh yeah, sorry, I forgot to say something. We are even more interested in the case where we continue the story, but here we oblige this singular leaf to come back to itself. Because when you do that, well, there are many phenomena that can occur. Either each regular leaf comes back to itself somehow, but it could be also what you call the self-eating snake, meaning, you see, it's like a snake eating itself. So you have a singular leaf, which is a circle like this, and all the regular leaves around, when they come back inside of themselves, and the story continues. This one goes like this and comes back inside itself, and so on. So the question is, I mean, how can we make a mathematical theory where this kind of relatively nice singular foliation would be examples? And there is a first attempt, which is perfectly fine, which is still used by several authors, that I will give under the name of smooth partitionifolds, that some author will call singular foliations, like David Miyamoto, Yael Leuchtkarshon, and others, for absolutely a respectable reason. And it's not the one I will choose. It's not going to be mine. But still, I present it because from a pedagogical point of view, it's very good. It's extremely clear and it's extremely practical to present it. So what is a smooth partitionifold? It's just a partitionifold L. So the initial manifold is made a disjoint union of sub-manifolds, but you crucially add this condition. If you take a point in L, like this point, well, you have the leaf through L, which is this manifold here. And what we ask is that if you take any vector tangent at this point to this leaf, there is a vector field around, call it U. Oops, sorry, call it U. We want that there is a vector field around which has a property that at every point it is at a tangent to the leaf where it is. You see? Like, so let me just repeat again. So a partition-unifold oops is said to be smooth when for every L and every tangent a vector, there is a vector field on M that goes through this tangent of a vector, which is always tangent to the leaves. Like in this case, yes, this exists. In this case, this exists. But you see, for the isolated lasagna, it doesn't. Because if you are on the lasagna and you take this vector, there is no way you can extend it to a vector field around that will be tangent to all leaves. Same thing here in the magnetic case. If you take this vector, there is no way you can extend it to a vector field tangent to neighboring leaves. So that's much better. But still, should we take it as a definition of a singular of a foliation? I would like to answer yes, because it's a very nice definition, but for some reason, it's not the definition that one. I will come to back after. Still, I will spend some time working on it because it has extremely nice structure that singular of a foliation defined the way I will do also have. And this extremely nice of a feature, we can say it in one word. It's this property, which is the most important. Traveling along a leaf is boring. What do we mean? It means that if we take a leaf, okay, well, maybe like of dimension 2, for instance, and you take 2 points on the leaf, well, and you look at what is going on in a neighborhood, like this point A and this point B. In a neighborhood where you have a smooth partition default again, so you have a smooth partition by leaves, and under this assumption of smoothness, you can show that in fact they are the same. So 2 points in the same leaf have neighborhoods where in fact what we have is the same smooth partition default. Is it clear, this property? Okay. And in fact, you can say more than that. Like I take my leaf like this. I take 2 points on the same leaf. I said A and B, so I call them A and B. And so I say that here, near here, and near here, we get in fact the same smooth partition default. But it has an extra consequence that if I take something which is across a section of the leaf, like this, okay, well, one can show that on each one of these cross section, I get an induced the smooth partition default, and one can check, that's crucial for what I want to say after, that these two are isomorphic. Let me come back to the self-eating snake that I had here. You see, if I take a point on the singular leaf and I take across a section, what do I see? What I see is, well, this point becomes a point like this, and the other leaves around become concentric as a circle. But if I take another point, I take also across a section, I will see exactly the same thing. Okay? But if I took this one, which was, well, every cylinder comes back to itself. I will see exactly the same thing. If I take a point here, a cross-section like this, what I will have is concentric as a circle, okay? So, long story short, if we have a smooth partition deformed, if you take a leaf, erase this, if you take any leaf, you have a well-defined notion of transverse smooth partition deformed. It's somehow the germs of smooth partition deformed that you get on some cross section, and it's well defined because you have this theorem that says that it is unique. Okay, this was to explain this item. I still want to explain this item. Oh yeah, sorry, I have explained these two items. I want to explain this item a little bit, so let me do it now. Well, again, take a leaf of a smooth partition deformed. Take a point, take any cross as a section. On the cross as a section, there is an induced smooth partition deformed. Well, in fact, locally, you have a direct product. So you have a little sphere here around this point, where what you have is, in fact, the direct product of the transversal smooth partition deformed times, well, just a leaf. Okay, it's just isomorphic to the direct product smooth partition deformed. Well, if you know Poisson geometry, you would not be surprised. If you know Lie algebroids, again, you would not be surprised. You have exactly the same type of a theorem for Poisson structures, or for Lie algebroids, or even for Lie group action on a manifold. Do you have any question? No?
And now you give a final definition.
Excuse me?
So I see that you give the first picture and the definition is not yet. Oh,
yeah.
Definition, yeah.
Yeah, no, I will explain, but in fact, it's not the definition we take. Okay. It's a bit strange. I mean, we could. Because this definition is very good. In particular, it's justified by a famous theorem called Chow theorem. But for some reason, it has lost. I will briefly explain why. And it's not exactly the definition we work. The definition that has presently won is this one. A singular foliation on a smooth manifold M, it's a subspace of the Lie algebra of vector fields. This means compactly supported. That's anecdotic. I will not say much. Which has satisfies free condition. It's involutive. It's a symmetry of M module. And it's locally finitely generated, which means for every M in M, there is a neighborhood U on which F restricted to U is generated by X1, XR with X1, XR in F. Well, here there is a small difficulty that I will carefully hide on what this means. Okay. I mean, when you see the definition like this, it seems quite unbelievable. I mean, why are we assuming that? So, but two things. What do we want to imitate? Well, we want to imitate what F should be thought of as vector fields tangent to the leaves, right? Because if you have vector fields tangent to the leaves, well, it's going to be involutive, it's going to be a symmetry of M module, and maybe if you are lucky to be finitely generated. But what is very annoying with this definition, when you see it first, I mean, it's really like extremely confusing, is that in this guy, there is no leaves, okay? When we define singular foliation, you expect to have leaves. And defined this way, it's some subspace of vector fields, compactly supported vector fields. There is no definition of leaves. But it's a theorem, an old theorem, that singular foliation admit leaves. But let me explain you what leaves are. Well, take MF as above. You can define an equivalence of a relation on M. I didn't say on M, like this. You identify 2 points if you have vector fields x1, xk in F, such that if I apply the flow, they are compactly supported, flows are defined. If you apply to M0 the flows of x1, xk, you get M1. What is good with this definition is that that's obvious. It is a partition of M. I mean, it's an equivalence of a relation, obviously. But you want something else on leaves. So we have F inside compactly supported of a vector field. So when you are given a point M, it's very logical to look at the subspace of TMM obtained by taking the value at M of all vector fields in F, right? That's the obvious thing you want to do. So like this, you have a well-defined subspace of TMM. And you want leaves to be sub-manifolds L in M that satisfy these for all points. Okay, but the good point with this definition is that leaves are manifolds. The bad point is that existence is not clear. Well, with this definition, well, existence is given. What is not clear is that it is indeed a partition, that it is indeed a sub-manifold. Well, it's a highly non-trivial theorem. There is even a long story of proofs with gaps and things like this. A theorem which has been somehow discovered and rediscovered many times. So Hermann in 55, then Nagoya in holomorphic context in 75. I could even add Dominique Cerveau in 76, and Androidakis Skandalis in 2003, and the list could continue. That says that these 2 definitions are equivalent, and that, in fact, the leaves of a singular of a foliation defined like this, leaves that can be defined either like this or like this, are what I just called a smooth partition manifold of M. I'm not going to say much about this, but this theorem can be interpreted as being a map from singular foliation to smooth partition manifolds. Be careful that this map is neither injective nor surjective. Well, what are the examples? What does it matter? We have many examples. Have Poisson manifolds, quadratropic submanifolds, Lie group action. All these can be merged as image of anchor maps through Lie algebroids. I mean, that's basically the Lie algebroid of a family of singular foliation. I don't know, can I assume anyone in the public is familiar with Lie algebroid? Or? Well, maybe not.
So we also have the transversion structure.
Excuse me?
You say that in the first definition of geometric way, you proposed by Cho, you have the transversion structure and the Weinstein splitting theorem, so that
yes.
this definition satisfies this property.
Exactly. Yeah. Yeah, I will come back to these properties very soon. Yeah, I'll come back to them very soon. And you have other classes of examples, those attached to affine sub-varieties. Like if I take an affine variety in Rn, or in Cn rather, I can take a vector field tangent to the fine variety, or vanishing on the W, or the tangent to the fibers of a polynomial map. Again, these are singular foliation in this sense. Last class of examples, I'm going to explain it now. Maybe I take one more slide. It's an important one. You work, let's say, on R2, and you take all vector fields that vanish quadratically at this point. At order greater than 2. This is a singular of a foliation. It's generated by this vector, this vector, this vector, this vector, this vector, and this vector. You see, as a safety of R2 module, obviously, it has to be generated by these 6 vectors. And it's a pure scandal that nobody knows the answer to this question. Are vector fields on R2 vanishing at order 2 at 0, the image through the anchor map of a Lie algebroid? It's extremely strange, but there is no answer to this question at this time. It's a general question which has been around for more than 30 years. Is any singular foliation the image of a Lie algebroid, at least near a point? With Thomas Strobl and Sylvain Lavaux, we had an answer through Q manifolds, and basically we are more or less convinced that the answer to this question has something to do with what Alexei Kotov would call a Q manifold. But it's not what I'm going to speak about this today. So just one word of why has this definition won? Well, it's because of non-commutative geometry. They use this definition of singular foliation, this one, oops, okay, the one that I have presented here. We really need this definition to study differential operators, like elliptic differential operators, and to do analysis with them. I mean, with this definition, they can get some C-star algebras, which are enough to prove index theorem, pseudo-ellipticity, KK of a theory, or more recently by Juncken and Omar motion, quite a few relation with hypoellipticity. And well, I'm not an expert on that. I'm not going to say a lot of things, but that's why this has won. Now, I want to come back to these theorems that I have presented. Oops, where is it? Here. Because, well, what I want to say is that I can change this statement and it's still true, like this. Let MF be now a singular foliation. Well, this remains true. If I have a leaf, if I take 2 points of the same leaf, I have like L1, L2, or it was A and B, sorry. Well, there are in a neighborhoods U and V on which F restricted to U and F restricted to V are isomorphic. Moreover, the isomorphism take this point to this point. So traveling along the leaf is boring, still holds true for singular foliation. This still holds true also. It's less obvious, but if I take a leaf, I take 2 transversals, and what I do is I take restriction, I call it sigma, I call restriction to a sigma of vector fields that happen in F that happen to be tangent to the sigma. And it can be proven that this is a singular foliation on the transversal first, which is unique, still holds true, meaning that if I take two transversals, I do the same construction twice, I take all vector fields in F that are tangent to this transversal, and I restrict them to this transversal, we get singular foliation, which are isomorphic. So these two items make sense if you have a leaf of the notion of transverse singular foliation of that leaf. Yeah, je suis en train de faire un exposé là. Plus tard, je suis en train de faire un exposé là. Yes, sorry. Yeah, on that leaf. Okay. Yeah. Sorry, where was I? Yes. So, and this is also true. I mean, you have a Weinstein splitting theorem that says that near any leaf, well, I said singular foliations are finitely generated. What can be proven is that you have generators, you have coordinates y1, yd, x1, xs, where generators, well, some of them are just purely in D. These are the ones which are along the leaf, tangent to the leaf. And the other ones are just purely in X. So you have functions X here and the other dx. So it says that you have generators of this form. Again, that's very similar to what Alexei would call Q manifolds, where you have exactly the same kind of theorems.
Camille,
yes?
I have a question. So these transverse leaves, you can take any leaf, or no, any submanifold, and you look just at those vector fields which lie inside them, and whatever you choose, it is isomorphic.
Well, let me a little bit more precise. So you take your leaf, and you take across a section, a sigma. Well, step by step. If you take n inside M, you can take restriction to n of all vector fields in F such that X is also tangent to n. Okay? This is a synth of n module, and this is closed under the bracket. Okay? Now, it may not be locally finitely generated. Okay. This may be not true. It may not be locally finitely generated, but if Tn and Tf add up to everything, then this is true. It is locally finitely generated. Meaning that if I take a leaf, L, I take two little disks transverse to it. Well, if they are chosen small enough, this condition will hold true, and I will have singular foliation here and there. Okay. Now, I have maybe to restrict them a little bit more, and then they will become isomorphic. Yes.
But the original singular foliation, if you just stay at one point in L, like say the left disk, if you choose the disk slightly different, you get still isomorphic.
Oh yes, I can take this disk or this disk, yes.
And is it so obvious?
No.
Okay.
No, it's not. No, it's not obvious. Yeah, no, it's not, but it's true.
Okay, thanks.
Again, not globally isomorphic.
Yeah, sure.
At the level of germs, it's isomorphic.
Germs,
Okay? What germs means you have neighborhoods of 0 where they are isomorphic. Okay. Okay, so why would I write low tech here? It's absurd. So, okay, long story short, yeah, I wanted to do it in 30 minutes. It took 35 minutes. It's quite okay. So if I have a singular with a foliation in this weird sense, that sounds extremely unnatural here. Okay, with these 3 items, involutive, safety of M module, locally finitely generated. If we take this example, leaves make sense. that I have explained a long time ago. Okay, leaves make sense, and also transverse singular foliations, they make sense. I mean, each leaf has a transverse singular with a foliation. Okay, so here I want to say slightly little more about transversal. In fact, I will elaborate on what Thomas has just asked. I mean, what is exactly a unique? We just said, so it's a very crucial point for my lecture today, but I will not enter entirely into that. So what is unique? As I said, unwell defined, therefore. So I just said it's a germs of singular foliation on R to the power codimension, so given a leaf L. On R to the power codimension of L at 0. And of course, it is a singular of a foliation for which the point 0 is a leaf, okay? But in fact, since it's unique at the level of germs, it's also unique at the level of jets, where jets means you take all of the formal jets, so yeah, of vector fields in the transverse singular foliation. So when you do that, you may lose some information. Like assume your transverse singular foliation is just R with this vector field at the level of germs. When you look at the level of jets, somehow you lose some information because this function vanishes with all its derivative at 0, and all you get is just, well, the singular of a foliation is a 0, okay? But the question that with Simon Raphael Fischer from the Taipei University, we decided to address is this question. Assume you take a leaf, assume you know a leaf, and assume you have chosen what's called a transverse model, with meaning we have taken a formal jet of a singular foliation on R to the power, like codimension of L. Okay. Well, how many singular foliations? Well, theoretically, I should say jets of singular foliations near L we can get. Okay. So the question we want to address, maybe I can say it in another way. We choose a leaf, we choose a singular choose a transverse model. So we choose a jet or a germs, at this point don't really matter, of a singular foliation near 0. Well, and you want to classify all singular foliations near L, of course, not far away from L, which have this leaf and this transverse singular foliation.
Camille, just to make it
Yes.
clear, so 0 is the leaf, not a point on the leaf.
Well, always this transversal, 0 has to be a leaf, yes.
You make a transversal only in one point on the leaf because they're morphic, or you take the whole leaf? That's the question.
So we take a leaf, which is a manifold M. Okay. And you choose, let's say to start with a germs, it's easier. And you choose a germ, and you choose, well, say, and you choose a singular foliation on Rn. Well, such that all vector fields, that's one thing we assume, all vector fields vanish at the 0. Okay. See, I choose.
So capital N is the codimension or what of the leaf?
Yes, yes. Okay, let's say it this way. You choose a manifold, L. I call it L. Later on is going to be a leaf. Okay, and I take a singular foliation on Rn made of the vector fields, I call it T. Well, Rn, in fact, in the neighborhood of 0 in Rn, such that all vector fields in T vanish at the 0, okay? And the question is, can we classify all singular foliation on a neighborhood of L in some manifold M, okay, whose transverse singular foliation is T? That's the precise question.
But given a singular foliation, didn't you say before that the transverse one is unique?
Yes, that's why I choose one.
So it's up to global issues or what? Like topology of the leaf plays a role or what?
Okay, implicitly, I assume the leaf is not like in a torus, an irrational slope. So to be more precise, okay, you are right. I have one more assumption, and such that L inside M is closed. We don't want to have irrational slope on the torus. Okay. Let me give an example. It will be easier. Okay. Well, if you take a regular foliation, then you have a well-known theorem that says that regular foliation were entirely classified by group morphisms. Why did I write maps here? It's group morphisms from the fundamental group of L to the group of germs of diffeomorphism of Rk. It's a theorem. This is called the holonomy map or the monodromy map. And this map entirely determines a regular foliation. Okay. If I can give another example, it's also known that vector bundles over L and vector bundles over L can be seen as singular foliation. To any vector of a bundle, we associate vector fields on E, which are at a tangent to the 0 section L. Principal of a bundles, which are basically the same thing in some sense as these, vector bundles, which are somehow the same thing as these, are entirely classified by GL dimension of E, rank of E, principal of a bundle. Okay. So roughly speaking, what it means is that if you want to classify, let me say it in a different way. Okay? It's not the way I wanted to say it, but oh, well, why not? If you are given L, and if you want to classify all singular foliations near L, where the transverse of a foliation is just by 0, so T equal to 0. then you are in fact classifying regular over foliations, and it's well known that those are classified by map from pi1L to germs of diffeomorphism of Rk. Now, if you want to classify for the same L, singular of a foliation for which the transverse model are all vector fields on Rn that vanish at this point, then in fact you are classifying vector bundles over E. It is exactly the same. And then what you get is G rank of E principal bundles over M.
So why vector bundles?
Because it's the same actually. Classifying vector over bundles over L, it's exactly the same thing as classifying singular foliation for which the transverse model is made of all vector fields vanishing at a 0 on some given vector space. You need to work a little bit for that, but you can see it is exactly the same thing. Okay. Okay, so so I went a little bit out of what I have planned to do. Let me come back to, is it clear to Thomas now?
Half.
No. Okay, at least let me give you a first statement, because it seems to be a bit hopeless, right? You have so many singular foliation. How can you really imagine to classify them? Well, here is a theorem that we proved with Leonid Ryvkin a few years ago. Well, if you have a singular of a foliation, forget this. If you have a singular of a foliation, and if your transverse, if you take a leaf L, and if the transverse a model is made of vector fields with no linear part, so vector fields that in some coordinates writes like this, with function here, I mean, this is not allowed for the transverse model. You want all vector fields to vanish at 0 with their derivative. Then we are able to prove that, in fact, it is a direct product. That if you have near a simply connected leaf, you have only one singular of a foliation where the transverse, if the transverse of a model is made of vector fields vanishing at least quadratically, and since you have only one, it has to be the trivial product. Okay, so in fact, it's not so hopeless. I mean, there is really a hope to classify them. So yeah, I have 10 minutes left, maybe even less. So I just give the main statement and the two main corollaries. So when you have a singular foliation, what we call inner symmetries, it's a group of maps from M to M, which are obtained by following flows of elements in F. Okay. What we call a symmetry, it's a map from M to F, that map F to F. And it's a non-obvious theorem that inner symmetries are contained inside symmetries. It's a subgroup, it's a normal subgroup. So you have a quotient which is called outer symmetries. Okay. In the formal setting, it's exactly the same. I take a formal singular foliation on, let us say, Rn, made of vector fields, of formal vector fields that vanish here. And we have an exact sequence that we call, I choose T0, a formal singular foliation. And we have an exact sequence like this, where here I take all of a formal diffeomorphism from Rn to itself obtained by following the flows of T0. Here, all formal diffeomorphism mapping to 0 to itself, and out the quotient of this guy by this guy. So we have a short exact sequence like this. And what we were able to show with Simon Raphael Fischer is that there is a one-one correspondence. Well, the theorem seems very abstract. I will not spend a lot of time on it. I will directly jump to two particular cases. Somehow, we were able to get a reasonably easy notion of infinite jets of singular foliation with a given leaf and a given transversal. It's the same thing as Galois cover of triplets made of like this. A Galois cover, so Galois cover, that's maybe a very French name, sorry. So it means you have L, you have L tilde. L tilde is connected, and pi 1L acts transitively on the fibers. So it's kind of principle of a bundle with discrete things. A Galois cover, a group extension where here you take inner of the transverse model. Here you take the group of the Galois cover. So it's in fact pi 1L divided by some normal as a subgroup. And you have an H here, but this H has to be inside symmetries of T. So you see, what you want to have, you have this thing here. What you want to have is a H here, so that the quotient is of the type pi 1L divided by K. Okay, it seems very abstract. And you have this H. And last thing you need is an H principal bundle here. Why? Where does it come from? Well, I would just write the keyword. It's groupoids. It's properties even of transitive groupoids.
The principal bundle is over L, I suppose.
Yes.
And this what you call Galois cover is just a covering map, no?
Yes.
Just
yes.
covering,
yes.
topological.
Yes. Okay. But a very important point is that because we work in the formal setting, and because the exponential map from vector fields vanishing quadratically at 0 to formal diffeomorphism with differential at 0 is the identity is 1-to-1. In fact, H principal of a bundle can be replaced by some quotient of it, which is of finite dimension, which is a finite dimensional Lie group. So in fact, this H principal bundle, they can be replaced on a case-by-case basis by a finite dimensional Lie group. It's a theorem that says that G bundle, in fact, if inside G you have a nilpotent normal as a subgroup, simply connected nilpotent normal subgroup, you can just forget it. It's exactly the same result here. So let me give you some corollaries. The first one is extremely disappointing in some sense. For me, it's the most surprising one. Oh, I forgot to say, so this we got through what is called something that both Alexei and Thomas created, and that Simon wrote about in his PhD. It's called Yang-Mills bundles. And somehow, it seems a bit weird, but what we are doing here, this classification, is just a particular case of a much harder classification of Yang-Mills bundles. If you're interested, Thomas, I can explain you the link after. But it's really like this idea. The transitive groupoid associated to this Yang-Mills bundle that Alexei and Thomas created some time ago. So, two corollaries. First corollary, if you have a simply connected leaf, very surprisingly, infinite jets of singular foliation with this leaf on a given transversal, it's the same thing of some finite dimensional principle of a bundle. And that's not very big. I mean, finite dimensional principle of a bundle, their classification is not that complicated. You have to look at the compact part, call it K, and you classify maps from L to B, K. I mean, like, I'm not saying it's easy, but it's known. And extremely surprisingly, although singular foliation seems to be completely infinite dimensional as a thing, well, they are not. We get back to somehow finite dimensional problem. Second particular case, it's when you have a transverse model which vanishes quadratically. So the transverse model is made of the vector fields that have no linear part. Then singular foliation around this leaf with this transverse model, let us forget this, is the same thing as group homomorphisms, well, up to conjugation, which is unnatural, from the fundamental group of L to outer automorphism of the transversal. And when you apply it to the, and well, again, it's really not easy to see it. I mean, and a particular case that I like a lot, if a leaf is a circle, then it's very easy to classify singular foliation. We take the transverse model, and it's classified by conjugacy classes of the group of outer automorphism of the transverse model. But what about the torus? What you need to have is some two outer symmetries, phi and psi, so that if I take the commutator of any of its representative, well, of course, I need to get an inner symmetry. But it's not exactly what I want. I want to have an inner symmetry, which in fact, I want to have an element of the universal cover of the group of inner symmetries. So, well, it's not an easy classification. By singular foliation admitting a torus as a leaf, it's eventually the same thing as some equivalence classes of pairs of outer symmetries that commute up to an inner symmetries plus an element of the universal cover of these inner symmetries. Seems very abstract, but somehow it's relatively, at least we have a classification. And I think I'm done. Thank you very much.
Thank you very much. Some questions?
Should I stop sharing screen, maybe?
Yeah.
Oh, my camera was off. I'm very sorry. I thought you could see me also.
So I just want to ask you the condition of vanishing quadratically is how up and down is that? You have a lot of examples of such.
Well, kind of like Poisson structures with a transverse structures that vanish quadratically. Well, at least I would say it's surprising. I haven't spoken much about existing literature. And like for Poisson structure, you have a lot of articles from Johann Marcotte, for instance, and his collaborators, who more or less always assume, well, that the corresponding symplectic groupoid is proper, or this kind of assumptions. I mean, weaker than that, but this kind of assumptions. And these kind of assumptions, somehow, they are opposite to transversally quadratic. They forbid transversal quadraticity. And we are very surprised to see that, like for Poisson structure, the case that looks totally impossible to deal with using, well, symplectic groupoid method, Sung linearization theorem, and Nguyen-Thien Sung linearization of a theorem, in fact, was kind of trivial because there's just a nothing, was kind of empty. Because at least at the formal level, it is empty.
But what I want to say as a remark, isn't it? I mean, on the smooth level, I think it's very, very difficult to treat these questions.
Right. There is at the smooth level, it's I would say almost impossible to have any hope of classification. Yeah. There are some that recently appeared by several authors. When you assume the transverse singular of a foliation is made of all vector fields on Rn vanishing at a given order, then absolutely independently from us, several authors got classifications. It's called B manifolds, the BK manifolds. Absolutely independent from us, but their results absolutely matches us. Michael Francis, for instance. Yeah, and it's studied for reasons linked to non-commutative geometry again. And their results are convergent. In this sense, they are stronger than us.
That's what I would probably wanted to ask, how much the analytical case is more complicated than the formal one.
Yeah, well, the thing that remains true is the abstract characterization with this 1, 2, 3. I mean, that's purely a group, that's purely Young-Mills thing somehow. I mean, you could replace with germs. Where is it? Like this big theorem, now I've put things everywhere. Oops, anyway, here. I mean, this part, this theorem, like infinite jets of blah, blah, same thing as this. You can do it for smooth partition manifolds. You can do it for groupoids. You can do it for algebroids. Somehow, it's kind of always true. You can do it for, yeah, and you could do it for your Young-Mills bundles. But no, sorry. Anyway, this is certainly true at the level of germs, for instance. What is not true is this fact that you can reduce to a finite dimensional principle of a bundle. This will not work anymore.
Okay, I see.
And that's crucial to say that for transversally quadratic, it's trivial. Because for transversally quadratic, in fact, transversally quadratic means that this bundle is just a point. Even that the group of this bundle is just a point. So if you cannot do this reduction, then it's getting very hard. Yeah. I think Leonid is working on it actually.
Okay. More questions to Camille? Okay, if no, then let me thank the speaker. It was very interesting. Thank you very much.
Thank you for inviting me.